Our fellow learners, this is Cameroon GCE O level, Chemistry 0515, June 2024, Paper 2, Section C. Here, in this section of your paper, you will need to write some short notes on a few questions. So, let's go to the question directly. Answer 2 questions out of 3. If you attempt more than 2 questions, only the first 2 will be considered. Where appropriate, equations and diagrams should be used to illustrate your answer. Write your answers on the sheet that follow section C. You will be provided a sheet. Okay, beginning with question number 8, it reads, list 4 factors which affect the rate of chemical reaction. The B part of it has 4 points for the A part. The B point, using suitable chemical reactions for each factor. Describe how the factor affects the rate of the chemical reaction. Good. That is the question for you. You are supposed to answer the question. Now, I'm going to start with question number 8. Now, list 4 factors. You know what is rate of chemical reaction. Rate has to do with something that goes with time. The rate of a reaction has to do with maybe the concentration with time, because it's something that has to do with time. The concentration that is used up in the chemical reaction per the unit of time that has been used, and it's usually per second. That is rate. So now they are telling us what are the different factors that will affect the rate of chemical reactions. Now, I have for you, I have about 5 different factors that can affect the rate of chemical reaction. I am going to list them out to you. Okay, let's say section A. 4 factors that affect the rate of chemical reaction include factors that affect rate of reaction. The factors, what are the factors? Factors that affect the rate of chemical reactions. Which are the factors? I can list them one after the other to you. One of the factors is changing the concentration of a solution. If we change the concentration, changing the concentration will affect the rate of reaction. One, that is concentration, the concentration of the substance. So changing the concentration changing the concentration of changing the concentration of solution. Okay, let me say, okay, change the concentration, the most important thing there. Now, 2, you can say concentration and then say, yeah, let's say concentration. Concentration. You can say changing the concentration of a solution. You can say 2. You can say pressure. And pressure goes only with gaseous reaction. For example, a gaseous reaction, like we're talking in Haber's process, in the production and also contact process. So changing the pressure of gases. Changing the pressure of gases. Yeah, changing the pressure of gases. Then we can talk of temperature too. Temperature is another factor that will influence the rate of reaction. Temperature. We'll discuss this as we go ahead. Temperature. Changing the temperature of the reaction. Changing the temperature of the reaction. We can. Another one is 4. These are your 4 points. Then the discussion will take 16 points. Now you can say temperature. We can say surface area. Surface area. Surface area. In that case, we are talking of like finely divided iron or and marble chips in a powdered form and in a lump form. So which one will react faster? So we said surface area. Changing the surface area of solids. Changing the surface area of solids. All these you will see more when I will be discussing them. Number 5, let me just give another one for you. Which one you'll be able to remember in the exam? Number 5, enzyme, adding or removing a catalyst. Could be enzyme or could be a catalyst. For in chemistry, we say catalyst. So we can say adding a catalyst. In that case, we can say adding. Adding or removing a catalyst. Adding or removing a catalyst. Adding or removing a catalyst. Including enzyme. Including enzymes. That is for biological reactions. Using what? Using collision theory. Using the collision theory. So now, fellow learners, we have factors that affect the rate of chemical reactions. Here we have concentration, changing the concentration of a solution. The concentration of a substance will affect the rate of the reaction. 2, pressure. Remember, we use pressure only for gaseous reactions. So changing the pressure of the gases will determine the rate of a reaction. Now, temperature. Changing the temperature will also determine the rate of a reaction, depending on whether it is exothermic or endothermic reaction. Surface area. Changing the surface area of solid, changing the surface area of solid particles or solid substances like your large sums of limestone or marble chips or what we call calcium carbonate. If it is broken down into smaller pieces, you increase their surface area. You are increasing their surface area. How it affects the rate of reaction. And catalysts, whether you add a catalyst or you remove a catalyst, will determine whether the reaction is going to be slow or fast. So these are the different factors you can list in the that can affect the rate of chemical reaction. Okay, the second section of it says, okay, second section, let's go there. The second section of it, of B part, says using a suitable chemical reaction. That's in each case. Using a suitable chemical reaction for each factor we have listed. Describe how the factor affects the rate of the chemical reaction. Good. We are here. We are going to choose different factors. The different factors, we are going to choose chemical. We are going to choose specific reactions, and we are going to choose equations to represent them and explain how these are affected. The factor affects the rate of reaction. So now, the B part of it is how does we are starting with concentration, and that is the B part of it. Yeah, yeah, B part, B, 8B. 8B is on 8B is here. 8B. 8B is 1. Our first factor was changing the concentration of a solution. How does concentration affect the rate of reaction? Concentration. How does concentration affect the rate of reaction? It should be noted that increasing the concentration of reacting solution will increase the rate of reaction, and decreasing the concentration of the reacting solution will also decrease the rate of the reaction. For example, now I said increasing the concentration will increase the rate of reaction, and decreasing the concentration will decrease the rate of reaction. I said increasing the concentration of reacting solution, increasing the concentration of reacting or reacting solutions, increasing the concentration of reacting solutions will increase the rate of reaction, and vice versa. Increasing the concentration of reacting solutions will increase the rate of reaction, and vice versa. And decreasing the concentration will also decrease the rate of reaction. Okay, I want to give you an example for this. My example is in the laboratory, we can use magnesium ribbon. We can use a magnesium ribbon. Magnesium ribbon is a metal. Magnesium ribbon reacts fairly slowly with dilute hydrochloric acid, but much faster if the acid is concentrated. Example, Ag magnesium ribbon Ag magnesium ribbon. I said magnesium ribbon. Excuse me. Magnesium ribbon reacts. Magnesium ribbon reacts fairly slowly. Fairly slowly with dilute hydrochloric acid, but much faster if the acid is concentrated. You will see that magnesium ribbon, which is a metal, if you put it, you take a conical flask and you put dilute hydrochloric acid in it, and you take the magnesium ribbon in the laboratory and you place the metal inside, the reaction is slow. Unlike if the hydrochloric acid was concentrated. So in dilute, it is slower. In concentrated, in concentrated acid, it is faster. So we now say increasing the concentration of a solution. What happens? The reaction is faster. And decreasing the concentration, what happens? The reaction is slower. Let me give an equation to represent this. You can place this as your equation. So here we can say magnesium that is solid plus let me just say this here. So it is magnesium chloride that is being formed. This is aqueous, it's dilute. The reaction would be magnesium chloride that is being produced. Let us see in solution aqueous plus a gas that is released, and that gas is a hydrogen gas. So this is an equation to represent that. Okay, let's go to factor number 2. The second factor is pressure. The pressure. In other words, you can still give another example for this for the purpose of revision. You can still say solid. Another example is solid manganese 4 oxide. Manganese 4 oxide is used as a catalyst. Manganese 4 oxide is used as a catalyst for the catalytic decomposition of hydrogen peroxide, releasing oxygen. The oxygen is given off much faster if the hydrogen peroxide is concentrated than if it is dilute. So that is another way you can put it like that. Another equation is another example. Example 2 for this. Example 2 for this, I said, like what I've just described, I have two, this is a hydrogen peroxide. Hydrogen peroxide, which is aqueous. Let's dilute hydrogen peroxide. It gives water. It gives water and a release of a gas, oxygen gas. Oxygen gas is being released. So, what is being used here? We are still talking of solution. We are talking of solutions. So I said this is another example I'm giving for this for the in terms of concentration. And there's another example I'm giving for in terms of concentration is that now I said solid manganese 4 oxide. This manganese 4 oxide here is used as a catalyst for the catalytic decomposition of hydrogen peroxide, releasing oxygen. You see, the oxygen, the rate at which this oxygen is being produced is somehow slower. Oxygen release is not released very fast. However, oxygen is given off much faster if this hydrogen peroxide was concentrated. So this oxygen is being produced faster if this is concentrated. But as it is dilute, oxygen is produced at a lower or a slower rate. That is just a second example. But the first example is better for the reaction above. I mean for the concentration above. Let's go to number 2. Number 2 is we are talking on the second factor we are going to be dealing with will be effect of pressure on the rate of reaction. Pressure. 2 is pressure. 2 is pressure. Pressure. We are going to discuss the effect of pressure on the rate of reaction. Now, it should be noted that increasing the pressure on a reaction involving reacting gases. What happened? The rate of reaction, it increases the rate of reaction. And decreasing the pressure of the reacting gases will also decrease the rate of reaction. In other words, changing the pressure on the reacting involving only solids or liquid has no effect on the rate of reaction. So I say here, increasing the pressure on gaseous reactions. Okay. Increasing the pressure on gaseous reaction. Increasing the pressure on gaseous reaction. Increasing the pressure. Increasing the pressure on a reaction. Let me say on a reaction involving gases. Involving gases increases involving gases. Increasing the pressure on a reaction involving gases increases the rate. Increases the rate of reaction. Increasing the rate of reaction. And decreasing decreasing the pressure of the reacting gases, decreasing the pressure of the reacting gases decreases the rate of reaction. Okay, said increasing increasing the pressure on the reaction involving gases increases the rate of reaction, and decreasing the pressure of the reacting gases also decreases the rate of reaction. Mind it should be mind you should also note that pressure has no effect when a reaction uh, pressure has no effect on reaction involving solids. Pressure only has an effect on what? On gaseous reaction. And increasing the pressure on gaseous reaction. Example is let me give an example here. An example is example. My example is this. I want to use the common one we have been using for the production of ammonia. In the industrial manufacture of ammonia by Haber's process, the rate of reaction between ammonia, between hydrogen and nitrogen gas is increased by the use of very high pressure. Okay, let me use that one as an example. My example is let me change the ink. I say I say uh, in in the industrial manufacture of ammonia, in the industrial manufacture of ammonia by Haber's process. Haber's process. By Haber's process. The rate of reaction between the rate of That's great. So here you can see here, my example is in the industrial manufacture of ammonia by Haber's process, the rate of reaction between nitrogen and hydrogen is increased by the use of very high pressure, which also improve what the percentage of ammonia in the equilibrium mixture. And the equation is like this. This is the equation you can find there. Because you have been asked to give specific example with chemical equations. So this is the equation you can find in that. So we have nitrogen gas plus usually 1:3. This is another gas that is being produced. It is in equilibrium. An equilibrium, and you have ammonium that is being produced. That is our example. That is example. Now we'll go to the third factor. The third factor is surface area. Let's go to surface area. Surface area. How does surface area affect the rate of a reaction? Okay, surface area should be our next factor now. Surface area. Okay, surface area. That is number 3. How does surface area affect the rate of reaction? Okay, it should be noted that increasing the surface area of a solid will also of a reactant. Increasing the surface area of a reactant, a solid reactant, will also increase the rate of reaction, and vice versa. So, for example, surface area is like this. The smaller the substance, the larger the surface area. The larger the substance, the smaller the surface area. So, when calcium carbonate is in lump, or marble chips, they are in lumps. When they are broken down into smaller pieces like flour, that is like powder. When they are broken down into smaller pieces like powder, they help to increase the surface area of the reactants. And that reaction is going to go faster than the reaction that is in lumps. So the larger the surface area, the faster the reaction, and the smaller the surface area, the smaller the surface area, the slower the reaction. Okay, let me say, increasing the surface area. Increasing the surface area will lead to increasing the surface area. Increasing the surface area of a solid reactant. Of a solid reactant will increase the rate of a reaction. Will increase the rate of a reaction. And vice versa. And vice versa. Increasing the surface area of a solid reactant will increase the rate of a reaction. And decreasing the surface area of that one too, the solid reactant too, will also decrease the rate of the reaction. Okay, for instance, look at this. Okay, we have particles like this. Smaller particles like this. Smaller particles like this. And larger particles like this. These ones, the smaller the particle, the smaller the particle, they have larger surface area. Larger surface area. These ones here, they are too large. Now they have a word. Their surface area is small. A small surface area. So the smaller the particles, the larger the surface area. The larger the particles, the smaller the smaller the surface area. Therefore, increasing the surface area will increase the rate of reaction, and decreasing the surface area will decrease the rate of reaction. Now, I want to give you an example of marble chips. Marble chips is an example I want to give you here. I want to give an example of marble chips for this reaction here. Okay, the example here is calcium carbonate. Calcium carbonate, which is solid, plus 2 HCl, that is aqueous. It will give you calcium chloride aqueous plus water yeah, and plus then plus carbon dioxide that is being released, CO2. So in this reaction here, these marble chips, the marble chips I've just given here, or the limestone, the limestone or the calcium carbonate as given as an example here. This in the laboratory, if we break these lumps of limestone into smaller particles like this, when we break them into smaller particles like this, like let me say in a powdered form, we are happy to increase the surface area of the particles. Therefore, this reaction is going to go faster, and carbon dioxide will be released faster. But if we leave this calcium carbonate in the lump form like this, having larger particles, now the rate of reaction is going to be slow, and only the gas will be released in a very slow rate. So that is an example. So now the fourth example will be, I'm going to talk on effect of temperature. I'm going to talk on temperature, how temperature affects the rate of reaction. Temperature. Temperature is number 4. Temperature, increasing the temperature. That is temperature. This how it goes. Increasing the temperature, you should know that increasing the temperature of a reaction will also increase the rate of reaction, and vice versa. Okay. Increasing the temperature increases the rate of reaction, and vice versa. Okay, I want to use an example of nitrogen monoxide and reacting with ozone. Nitrogen monoxide reacting with ozone. Remember, at 10 degrees, at 10 degrees, at 10 degrees, a 10 degrees increase in the temperature of a reaction will also increase the number of molecules. When in a reaction, when a temperature is increased by 10 degrees, know that that increase in 10 degrees is going to increase the kinetic energy of the particles. That 10 degrees increase of a temperature does what? By doing like that, reacting particles will acquire more energy, more kinetic energy. So more particles are now going to acquire more kinetic energy, and there's going to, the rate of or the frequency of collision of the particle is going to increase. So in that case, we can say a 10-degree increase in the temperature of a reaction will increase the number of molecules. A 10, we can say a 10 degrees Celsius increase in the temperature of a reaction increases the number of molecules increases the number of molecules the molecules that will acquire with enough, I can say enough kinetic energy, with enough kinetic energy, with no kinetic energy, which kinetic energy which is equal to the activation energy, which is equal to the activation energy, which is equal to activation energy, resulting in what? Resulting in more frequent successful collision. Resulting in more frequent successful collision. Collision that leads collision excuse me, a collision that leads to a faster reaction rate. I want to give an example of nitrogen monoxide with ozone in the depletion of the ozone layer. An example is nitrogen monoxide reacting with ozone, and this causes the depletion of the ozone layer. We have example is NO, which is a gas, plus this is the ozone layer and threatening human life. To give nitrogen NO2 plus and oxygen. So, this example, I'm saying that the reaction of nitrogen monoxide with the ozone layer, with the ozone in the depletion of the ozone layer increases the increasing global temperature. So when this react there, that's what happens there. So precisely, effect of catalyst. Let me give you the last one. Effect of catalyst. You could use it. Number 5, catalyst. Do you know that one? Catalyst. Catalyst. Okay. The effect of catalyst. How does catalyst affect the rate of chemical reaction? I'm going to give you a series of examples for catalyst. 1. Adding a catalyst increases the rate of a reaction. Adding a catalyst will increase the rate of a reaction, while the removal of catalyst will slow down the rate of a reaction. So now, what is the role of this catalyst? When you add a catalyst, it increases the rate of reaction. When you remove a catalyst, it slows down the rate of reaction. The question now is, what role is the catalyst playing in a reaction? A catalyst increases the rate of a reaction by providing an alternative pathway. That is, by lowering the activation energy for the reaction. And lastly, the catalyst, it remains unchanged at the end of the reaction. It is not used during the reaction. Again, increasing the rate of reaction when you add a catalyst, you decrease the rate of reaction when you remove a catalyst. Now, the catalyst help to do what? It help to increase the rate of a chemical reaction by providing an alternative pathway for the reaction. And this alternative pathway is what? It helps to lower the activation energy for the reaction. And the reaction goes faster. And it should be remembered that at the end of the reaction, the catalyst is not used up. Let me give you some series of examples for that. Examples. I don't need to write again. Let me just give an example to you of catalyst used in increasing the rate of reaction. Catalysts that are used in increasing the rate of reaction. We have for ammonia, number 1, A. I can say A for the production of ammonia, N2 plus, that is a gas, plus, in the production of ammonia, it is in equilibrium. And equilibrium, you will have ammonia that is being produced. Ammonia is being produced. The ammonia gas is being produced. And this is Haber's process. And in this Haber's process, what is the catalyst that is being used? The catalyst used there is what? Is a finely divided ion. The catalyst is a finely divided ion. A finely divided ion catalyst. A finely divided ion catalyst. The second example is in a contact process in the production of sulfur trioxide. Here you have sulfur dioxide, which is a gas, plus oxygen, which is also a gas. And it goes now to do what? It goes to produce sulfur trioxide. Sulfur trioxide, which is still a gas too. And what process is that? It's contact process. This is contact process. And the catalyst used in this case is which catalyst? The catalyst used here is vanadium 5 oxide. We call it vanadium pentoxide. V2O5. Vanadium pentoxide. Vanadium pentoxide. So we call it vanadium 5. Vanadium 5 oxide. That is the catalyst that helps to increase the rate of reaction here. And the last one here, our problem has changed. The last one here is the last one here is the last one which I want to give here is the last one here is excuse me. Yep. The last one here is the catalytic decomposition of hydrogen peroxide. I think I mentioned it in the other example. Catalytic decomposition of hydrogen peroxide. We have hydrogen peroxide. Hydrogen peroxide. Hydrogen peroxide. Now, when it is being decomposed, we have water that is being produced. Water is released, and oxygen. And the oxygen that is being produced. Hydrogen is being produced. This is, we call this, the catalyst here. The catalyst here is manganese 4 oxide. The catalyst here is manganese 4 oxide. Manganese manganese 4 oxide. With all this, if you provide all of this, you are likely going to have all your scores. So, fellow learners, let me go again and give you the same. So you have 5 different factors that can affect the rate of reaction. We talked of concentration, pressure, changing the temperature, surface area, catalyst. And we started with with concentration by saying that increasing the concentration of a reacting solution will increase the rate of a reaction, and vice versa. We're using magnesium reborn in acid. Increasing the concentration of the acid will increase the reaction, as I explained. So if the reaction, if the hydrochloric acid is concentrated, more of the gas is going to be produced very fast. The reaction is going to go faster than it is in dilute acid. Then we went further again on pressure. Pressure affects but only gaseous reactions. Okay, and in this case, increasing the pressure on the reaction will involving gaseous reactions. Will increase the rate of reaction, and decreasing the pressure of the reacting gases will also decrease the rate of reaction. I was giving the case of hydrogen and nitrogen in the Habermas process. I gave an example. Now we go again on surface area. I said increasing the surface area of solid particles. in a reaction will also increase the rate of reaction. I gave you the smaller the particle, the larger the surface area. The larger the particles, the smaller the surface area. I use marble chip or what we call limestone or calcium carbonate as an example that increasing the surface area of limestone particles will also increase the rate of reaction. Now, I went further for temperature. Temperature now is also another factor that also helps to increase the rate of reaction. How this happens? Increasing the temperature, that is increasing the temperature, increasing the rate of reaction and vice versa. A 10-degree increase in the temperature of a reaction will increase the number of particles with enough kinetic energy, which is equal to the activation energy, resulting in more frequent successful collision that leads to a faster reaction rate. I gave an example of nitrogen monoxide reacting with ozone and leading to nitrogen dioxide, and this is what's leading to the depletion of the ozone layer. The last factor was the catalyst. I was trying to use a catalyst. Adding a catalyst into to a reaction will increase the rate of reaction, and removing the catalyst will decrease the rate of reaction. I gave an example. There are 3 examples I've given here. I have given you an example, the Haber's process again, and we use but finely divided ion in it. Finely divided. How do we say it is finely divided? The ion particles are chopped into smaller pieces. When they're chopped into smaller pieces, so that the reaction will go faster, and this helps to increase the rate of reaction in the production of ammonia. Again, I also use in the contact process. I also use vanadium 5 oxide, which is also a catalyst in the reaction in the production of sulfur trioxide. And lastly, I also use manganese 4 oxide in the decomposition. Of what? In the decomposition of hydrogen peroxide. So these are good examples you can give when it has to do with this question. Thank you very much. Take your time, go through this, and you will have something good. So we will be starting with the next question when we come back. Thank you very much. Thank you. For those of you who have not subscribed to this channel, take your time and subscribe so that subsequent videos, you will be having them. My goal to you is that you understand the basic concept in chemistry so that you become, when you go, you can become good engineers, you can become medical doctors, schools of pharmacy, aerospace engineers, educators, and whatever you desire in life. Thank you. Bye-bye.